Let's look at an alternate approach to compute the same formula 3 to the power 644 mod 17. Now this approach will appear to be a little bit more complex, but it's going to be much more efficient. So first I'm going to write 644 as 512 plus 128 plus 4. Note that the numbers that we chose are powers of 2, and the way we would go about finding these numbers is by doing base conversion to base 2, and that will give us the numbers that are needed. So let's focus on the second step. The second step is going to ignore what happened in part 1 pretty much. It's just going to look at the highest power we needed, that was 512. So what it's going to do is it's going to start with 3 square, which is same as what we did before. It's going to do that by computing 3 square as 3 times 3. Again, the answer would be still 9. The next step, instead of finding 3 to the power 3, we are going to find 3 to the power 4, and we are going to do that by taking a square of the previous terms. So in that case, I will have 9 times 9, that is 81. If I do modulo 17, it's going to give me 13. I keep going ahead. So here I'm going to square 3 to the power 4 to get 3 to the power 8. I'm not going to go bother finding the answer, but I want to see how many multiplications I would need to get to 3 to the power 512. So let's look at here. I have 1, 2, 3, 4, 5, 6, 7, 8, 9. The number of multiplications I needed was going to be 9. And actually I could have figured it out faster if I had observed that 512 is really 2 to the power 9. Part 3 is going to be combined parts 1 and 2. So 644 was written as 512 plus 128 plus 4. So that means 3 to the power 644 is going to be 3 to the power 512 times 3 to the power 128 times times 3 to the power 4. Note that what we did earlier was we computed 3 to the power x, where x was a power of 2. So that means what we did on the previous slide, we have found the answers to all these questions. So we're going to take those, and I will need the number of multiplications in this case to be 2. Note that the number that we need here would be varying depending on the exact number that we were working with. So for example, 644 consisted of 3 powers of 2, so we needed to do 2 multiplications. On the other hand, if the number was just say 512, then we wouldn't have to do any multiplication. If the number was something like 512 plus 256 plus 128 plus 1, which is basically 1023, I will need to do 9 multiplications. So right now I had to do a total of 11 multiplications, but it could grow to 18 if the number was slightly different. Instead of it being 644, if it was 645, it might change, 643, it might change. But for all numbers up to 1024, or rather 1023, the number of multiplications I will need could grow, but no more than 18. And this is going to be the key for doing modular exponentiation that we need to do in the context of cryptography. Now the key here is the number of multiplications I needed was significantly lower than what I needed for approach 1. In approach 1, I needed 643 multiplications. Here I needed no more than 18. So the approach 2 can be summarized as follows. First, convert the exponent into a binary format. This is something we saw earlier. To find the relevant powers of 2 that you need to compute. Part 2, put part 1 aside and just compute b square, b to the power 4, b to the power 8, 16, 32, and so on and so forth. Part 3, combine the relevant powers you needed to get to the final answer. Note that at every step, we should use mod operation whenever possible to ensure that the numbers that we're dealing with are always small. Once again, we have reached the check before you go ahead slide. How many multiplications would be needed to compute the expressions that I have on the slide? For simplicity, you can assume that 2 to the power 10 is roughly the same as 10 to the power 3. That will make your analysis simpler.